Okay, this lecture is going to start into Chapter 6 of the curriculum. Chapter 6 is entitled The Network Layer. The network layer is Layer 3, and at Layer 3 is where we have IP addresses. So we're going to be talking about the end-to-end communications, possibly off the local network, and we will be communicating using IP addresses at Layer 3. I'm sure you know by now at Layer 2 we use the MAC addresses, which are only valid on the local area network. So, like most chapters, this starts with an activity called the road less traveled. You should, I am going to assign this due in 1 week, but important thing that it points out in the graphic is there may be many different paths that your IP packets can travel through to make it from the source to the destination. One of the things, we talk a lot about addresses, but notice that the graphics points out sequence numbers. So as we know from before, a message is broken into different segments, and then those segments are encapsulated in IP packets and sent across the network. So if they take a different route, if we send packet 1, 2, 3, 4, 5, 6, it may show up as 1, 3, 2, 4, 6, 5. That's not super likely, but it is possible, and it is important to realize that when we talk about it. At the network layer, the other thing in the bottom portion of the graphic, there are 4 basic things that we care about or concentrate on at layer 3. That's addressing end devices, and again, we'll start talking about IP addresses a lot more. It encapsulates data from layer 4. Also, routers are referred to as layer 3 devices. That is, they do routing. They do that routing based upon destination IP address. And then if we are receiving a packet, then it's responsible of de-encapsulating the frame to look at the IP packets and deal with those. So I will sign this activity. Watch for it to appear in Blackboard. So this graphic is showing all 7 layers of the OSI model, both on the host and, the source on the left, the destination on the right. So we're going to play the animation. Basically, this will show what I talked about previously on the activity. So these 2 hosts want to communicate with each other. There's data that it would like to send. So it goes through, and as we've talked about recently, the PDUs for layers 5, 6, and 7 are data, data, data. When you get down to layer 4, what it's going to do is it's going to break that data into a segment, and it's going to encapsulate it into an IP frame. That IP frame is going to go down to layer 2 and be encapsulated into an Ethernet frame. That frame will go down to the physical level, which is responsible for putting the 1s and 0s of that frame onto the internet or the network. It will travel through possibly a number of routers, and then when it arrives at the destination, the physical layer will pull the 1s and 0s up. They will read that as a frame. They then pass the frame up to the data link layer. The data link layer will de-encapsulate the frame and have the IP packet. That IP packet will be passed to layer 3. It'll be de-encapsulated there, where we end up with a segment. That segment will be passed up to layer 4. The segments will be de-encapsulated, and then we have data, data, data that ultimately makes it up to our destination host. And the 4 things over here, like I said, I mentioned previously, but those are very important to understand the characteristics and function of layer 3. Now then, at layer 3, there are a number of protocols. But in this text, and when we're doing Cisco networking and the OSI model, primarily what we care about is IP version 4 and IP version 6. As I said previously, if I simply say IP, then I'm talking about IP version 4. We will talk about IP version 6 and why we need it. In the note here, they said there's some other legacy or older protocols that are not shown because they're not discussed. I think we may have seen these in a graphic in chapter 1 or 2, but some examples of that would be Novell IPX, AppleTalk, and DECnet. But like I said, those are considered legacy protocols, and really what we care about is IP and IP version 6. Okay, so we're talking about encapsulation. Basically, we would be getting a segment from layer 4, and we would take that segment and put a header on top of it so that we could transform that into an IP packet. So that's what that's showing here. We put an IP header on to the segment that's been encapsulated, and that becomes the data of the IP packet. Okay, several characteristics of IP or the IP protocol that is important to understand. They are connectionless, best effort, and media independence. Those three will be discussed in the upcoming sections. So we'll start with the fact that IP is connectionless. They're drawing an analogy to the Postal Service. Analogy of a Postal Service, I think we've seen that once before, and it works really well for some of the concepts in this networking class. But the analogy is a letter. You're sending it to someone. Once you place the letter in the mailbox, you do not know if the person receiving the letter is at home when the letter arrives, 1, 2, 3 days later. We don't even know that the letter arrived for sure. We don't know if it's not there yet, it's still in transit, or maybe it was lost or something like that. And when the letter shows up, we don't necessarily know if the reader has read or can read the letter. The other thing that happens is even if you tell the person you sent the letter, they don't know exactly when it's coming. Now, they may have some idea like, when you mail me something from, state X, it usually takes 3 days to get here. And those 3 days would be a particular day. And oh, by the way, our mailman or mail lady shows up at 2 p.m. So we suspect we might get the letter around 2 p.m., but we don't know for sure. So that's kind of the same thing when we send an IP packet, which is shown here. We don't know if the machine is on the network. We don't know if and when the IP packet actually arrived to the destination, and we don't know if it was able to decode and read and understand the contents. The other thing that is the case in this is any given machine, in this case the machine on the right, which is the recipient, doesn't even really know a packet's coming. It's just all of a sudden, oh, hey, there's a packet that's being passed to me from layer 2, because I assume it's either a broadcast or it was a frame destined for me, therefore the packet is destined for me. Best effort delivery. This sometimes surprises people if they haven't been exposed to this or when we first talk about it, but there is no guaranteed delivery of IP packets at layer 3. A packet is sent, routers route that packet, hopefully the packet makes it to the destination, hopefully it makes it there in the correct order, but as the graphics is showing here, things are lost. Now, they're saying that's an unreliable network layer protocol. That doesn't imply there's lots of problems and lots of packets are lost, but it's important to understand that that can be the case. There is nothing at layer 3 to ensure that packets make it to their endpoint. And then the third aspect, media independence, we've talked about in a prior chapter. Basically, we have Ethernet, and you'll notice that the packet first goes over copper Ethernet, then over a copper serial connection, then over a fiber optic connection, then over copper Ethernet again, and then finally wirelessly to the destination. So every way through here we have an IP packet. It doesn't really matter what type of media we're going over. So I think before we were talking about Ethernet being media independence. Well, IP, which rides on top of Ethernet, is media independent as well. This is an activity that you can do on your own related to the characteristics that we just discussed. So moving on to 6131 and talking about those headers. We've been talking since, I believe, chapter 1 about the fact that we often add headers and sometimes trailers when we're going through the encapsulation process. So when a segment is coming down from layer 4 to layer 3, it is encapsulated. So down here at the bottom, this would be the data of our IP packet. We know that there's a source IP address, destination IP address. It's important to start learning, if you haven't already, the fact that an IP version 4 address is 32 bits long. So each of these are 4 bytes or 32 bits. And then up here at the top, we have some other information. The version is half a byte. Sometimes half a byte is referred to as a nibble, but it's 4 bits, and therefore it can go from 0 to 15. The version of IP that we've been using for decades is IP version 4, so there would actually be 0100 encoded in this to say this is IP version 4. We've mentioned IP version 6. In the case of IP version 6, this field would, or this version portion would be 0110, the binary representation of the number 6. We're then going to have the length of the header, and then there are a number of other things, like differentiated services is used for priority. See, time to live down here. We may have mentioned this in passing before, but most of the time when an IP packet is sent, at least IP version 4, this is set to 255, the largest value that can be held in 1 byte or 8 bits. That's all the bits set to 1. Every time this IP packet goes through a router, this value is decremented by 1. If that value ever hits 0, the packet is returned to the sender as undeliverable. And that doesn't happen a lot unless there is something called a routing loop. The protocol basically tells what type of packet we have. If this is hexadecimal 1 in the protocol, that means we have an ICMP packet, an Internet Control Message Protocol. In your text, if you see 0x in front of a number, that means it is a hexadecimal value. So for example, for ICMP, it would be 0x01. If it's a TCP packet, from the layer above, it'll be hexadecimal 06. And if it's a UDP packet, it'll be hexadecimal 11. Now, I know I've mentioned UDP and TCP, and we may have talked a little bit about TCP, but as we go on and start talking about layer 4, we'll talk about those in much more detail. And then, of course, I've already mentioned the source IP and the destination IP. There are some other fields that I don't know if the textbook talks about, or at least talks about right here. One of them is the internet header length. This is 4 bits in length. It specifies the number of 32-bit words that are in the header. So what they've shown you is this graphic is basically 32 bits wide, and it's telling you how many of those we have. So in this case it would be 1, 2, 3, 4, 5. So the value would be set to 5. The total length is 16 bits. That specifies the total length of the entire packet. And when we say entire packet, we mean all the header and all the data that is in the IP packet. We talked about checksums for Ethernet frames. We have something here called the header checksum. Basically, that checks that all the information in the header is intact, and in this case it's 16 bits instead of the 32 for the frame check sequence. And then if the packet is fragmented, that means broken into pieces, we have an identification which uniquely identifies the fragment. And then we have flags that indicate how the packet was fragmented. And you can say, you may fragment this, do not fragment it, this is the last fragment, or there are more fragments. So that's some of the values that will be there. And then finally, the fragment offset that we have here is 13 bits, and it is the fragment order. So those are all the pieces, I believe, that are displayed in the header. This is a video showing IP headers in Wireshark. I typically let you watch these outside of class, but I think there's some things in here that I want to discuss. So we'll make an attempt to play this, and I may pause it and discuss as we go through here.
Let's see how network layer information can be seen and analyzed in a Wireshark packet capture. I have a screenshot from a Wireshark packet capture, and you can see that the second packet that's been captured has been highlighted, and then in the packet details window, the network layer information.
So the one important thing that hopefully you're learning about Wireshark is the fact that it will go through and decode packets for you. You know, even simple things like taking a 32-bit number and converting it into an IP address, telling you what protocol is being used, that type of thing. And then also down here we have different things. Probably previously you've looked at the Ethernet label or the Ethernet layer where it decoded things within an Ethernet frame. Here they have expanded the IP version or the IP protocol version 4 packet. Version number set to 4, the header length is 20. So all those things I just took about, it's reading the binary values and displaying that to you, including like showing you the frame check sequence and telling you that yes, the frame was intact. So this is one of the super nice things about Wireshark.
Has been expanded to show us all of the things happening at the network layer. So let's see what's happening in this particular packet that we're examining. We can see that, first of all, the network layer protocol or internet layer protocol that we were dealing with was Internet Protocol version 4, IPv4. We can also see that the source IP address was 192.168.1.109. You can see it also highlighted up here in the packet list window area, and that the destination IP address was 192.168.1.1, and we can also see that up here. We can see that at the higher layer, this is a TCP protocol packet, but if we limit ourselves to just the IPv4 fields or the IPv4 information, we can see the different types of control information that's contained in every IPv4 packet. For instance, the version number, which is 4, identifying this as an IPv4 as opposed to IPv6 packet. the header length, or the length of the header. This is the minimum size of an IPv4 header. The differentiated services field, which is used for packet prioritization and is useful for applications like voice over IP. The total length of the packet. The identification number, which is used for fragmentation. The flags, you can see that the DF bit has been set, which stands for don't fragment. This packet is not large enough or is not identified for fragmentation. Fragment offset. The TTL, or time to live, which is set to 128. Every time a packet is routed from one hop to the next, the TTL number is reduced. When the TTL number reaches 0, the packet is dropped, ensuring that packets don't circulate on the internet forever on an endless loop. The TTL value is also used in ICMP trace routes and pings. The protocol field lets us know the type of information to expect in the data portion of the packet. A 6 identifies the data portion of this packet as being a TCP packet. The header checksum field, which allows routers to check to see if there are any errors or inconsistency in the IP header. If there is, the packet will be dropped. And then lastly, the source and destination IP addresses, which are the most important part of the IPv4 packet. Let's take a look at 2 more screenshots of Wireshark packet captures, and we'll see some similarities and differences. The next screenshot shows us that now we're looking at the 8th packet captured. The packet's source IP address is also 192.168.1.109, and the destination IP address is 192.168.1.1, except this packet is an HTTP GET request. So this is a request to a web server located at 192.168.1.1. You can see that the network layer or internet layer information has been expanded, that it's also the IP version 4 protocol, and that we have similar information in the different fields. Notice under the total length field that this packet is 411 bytes compared to the previous packet, which was only 52 bytes. You can tell that this packet has a lot more information, or is a much larger packet than the previous one. If we look below the Internet Protocol version 4 information, we can see the TCP information, and then below that there's Hypertext Transfer Protocol, or HTTP protocol information in this packet as well. I'll move forward to the next packet, and you can see that this packet is the 16th packet captured right up here. It's also from host 192.168.1.109 to host 192.168.1.1, except this is the ICMP protocol. You can see from the information in the packet list window that this is an echo or ping request. If we look in the Internet Protocol version 4 information in the details area, we can see some minor differences. The version is still 4, the header length is still 20 bytes, but we can see that the flags are slightly different, and that the protocol field is now set to 1, indicating that the data portion of this packet is an ICMP protocol message. Notice that in the details window at the bottom here is an expanded area to look at the header information specific to ICMP.
Okay, one thing I wanted to mention here is I believe all the videos have a click here to read the transcript of this video, and I suspect most of the time that people would rather go back and actually just watch the video again instead of reading, in this case, a 5+ minute demonstration. But the one thing that's nice about this one is notice right here, click here to download a PDF that has the Wireshark captures and notes that were used during this demonstration. So I think that might be useful for you to be aware of and to possibly look at when you're going back and reviewing this section of the curriculum. 6133 is an activity related to the different types of IP version 4 fields and what their function is. These will appear over here to the right, and then you can put each header, click on the IP version 4 header field down here in which it belongs. Okay, so what are some limitations of IP version 4? IP version 4 was created in the early 70s, and in that point of time it allows for something like 4.1 plus billion IP addresses. So back in the early 70s, when there were a handful, 5, 10, 15 hosts on what became the internet, the fact that they had 4.1 billion of these was just crazy, crazy, crazy big. But because of a number of reasons, we have effectively run out of IP version 4 addresses. So IP version 4, we hit the limitation of how many addresses there are. The other thing is routing tables that are used. You have an entry for each network, and as the internet has gotten bigger and bigger, the routing tables grow, and when the routing tables grow, that means we're using more memory on the routers, and also CPU on those routers. So we're asking more and more from our routers, kind of from a computational memory standpoint. And then to solve these problems, a lot of times we use NAT. There are different reasons we might want to use NAT. In this case, it would be to help with the depletion of IP addresses, but you probably use NAT in your home. If you have a ISP and you have a multifunction device from the ISP, and you have more than one machine in your home or one device that is capable of talking IP. I have laptops, I have TVs that talk to it, game stations that have IP addresses. If you have a smartphone, each of your smartphone is going to have an IP address. My wife does QA, tests a lot of mobile devices. She has like 10 cell phones that she has to test. They're all on our wireless. And I'm sure there's some other things. Oh, our Nest thermostat is on there. So, I probably have 20, 30 plus devices in my house that need IP addresses. And what happens is your multifunction device gets a single public IP address from your ISP, your internet service provider, and then all the IPs in your house have private addresses, and then they use NAT so that they can all communicate. So basically what happens is NAT stands for Network Address Translation, and when you send a packet to your favorite website, what happens is the multifunction device records your internal to your house private IP address, who you're talking to, what port you're talking to them on, and what port you're talking from, and then it relays that IP packet, and as the source IP, it puts its IP address because it's a public IP address. That allows the packet to travel to the destination. If the destination responds, it'll come back to your multifunction device, which will then look at the port numbers and determine which device in your home that frame needs to go to, that packet needs to go to. And then what it will do is it will make itself, it will change the destination IP to be the internal IP address on your home. We'll talk about NAT more, but another problem is NAT in some cases can prevent end-to-end connectivity. So that was kind of a long discussion on this section, but those are some of the limitations that we have to worry about with IP version 4. So how do we solve those? Well, we come out with IP version 6. Now, you may think of this or you may not. There was an IP version 5, and it primarily dealt with quality of service, and it was never really used. So then when they came out to solve the limitations of IP version 4, it already used IP version 5, so okay, this is IP version 6. So this is trying to tell you about the address space, but before we do that, let me give you some more information. So when did they start looking into a replacement of IP version 4? Because they knew we were going to run out of IP addresses. The Internet Engineering Task Force actually started looking at this in the 1990s. The one big thing, IP version 6 solves a number of problems, but one big one is what's referred to as address space. And they're trying to show you how big of a number as far as host we have. So, right now, put like 4186, some other numbers here, I believe, 4 billion. That's how many we have now. That's maybe a number you can kind of imagine. Down here, undecillion with something like 30 zeros after it, that's a little hard to imagine. I think your textbook somewhere says it's the same as the number of grains of sand on planet Earth. Well, where is there sand? How thick is it? Does that really tell you anything? If you take a quart jar and scoop it up, how many pieces of sand are in there? It's going to be very difficult to count. So I did some calculations, and what I came up with that I think might be a little easier to visualize is that if we took square meters, every square meter on the surface of the Earth, and that surface of the Earth would include land and water. So think about a meter squared. In that meter squared, with IP version 6, for every meter on planet Earth, there are 0.6 million billion IP addresses that you could have in that square meter. And there are a lot of those square meters on the planet Earth. So that may let you visualize it a little easier than the number of grains of sand on planet Earth. Some things they mention over here after increased address space. Now, IP version 4 is 32 bits. I just mentioned that. It's also important for you to learn that an IP version 6 address is 128 bits. So 4 times as many bits, but exponentially bigger as far as the number of addresses we can have. They did some things to improve the IP packet handling. They reduced the number of header fields. However, they allowed for additions of extensions. So if some networking company need to extend the way IP version 6 packets worked or wanted to put more information in the packet, they could do that through extensions. And they did this for increased scalability and longevity. Now, we had 4 billion addresses, which was crazy big in, 1970 plus or minus a little. So here we are almost 50 years later, and we're just really running out of IP addresses. So it took us 50 years to do that. Now, we're sitting here thinking, okay, 1 with 30 zeros or whatever that is, that's a really, really big number. Probably we'll never run out of those. But, 50 years from now, somebody may go, oh, those idiots in the early 2000s thought that IP version 6 had enough addresses. And with all the crazy stuff we've done in the 50 years since then, we're running out again. Or maybe it'll last forever. It's hard to say at this point. I'm sure in 1969, 1970, when they had 3 hosts on the internet, they never thought they would run out of 4 billion. We have so many IP addresses that we can give every machine a public IP address. And if we can give every machine a public IP address, then there's no need for network address translation, NAT. So that's a nice thing we do with that. And then finally, there is security and authentication and privacy built into the IP version 6 protocol, things that have become issues since the IP version 4 protocol was first created, like I said, in 1970, plus or minus. Okay, so here we're talking about IP version 4 headers. We've seen that before. Then here we look at IP version 6. So if you look at this, the actual header itself is close to the same size. The reason being is there's now 128 bits in your source address and 128 bits in your destination address. But up here, the number of fields has become much less. So let's talk about some of the advantages. So we have a simplified header, therefore we can have more efficient packet handling because there's not as many things to look at. We increased the size of the payload or the data that can be sent. We still have routing, but because we have a hierarchical network architecture, we can have some routing efficiencies. And then auto configuration for addresses, and then elimination of the need for NAT. So those are some of the things. The other thing to note is that there is no checksum in the header as there was with IP version 4. Okay, so let's actually look at this in a little more detail. We still have the 4 bits here for the version. So version 6 again would be 0110. That's 6 in binary. Traffic class relates to quality of service, which we talked about as the fact that some packets, such as streaming video and voice, may be more important than other packets, such as email message or a web page. We have something called a flow label. Flows have become very important in network analysis and in security issues or debugging. Basically, what a flow, if you have a conversation like I talked back and forth a number of times, my web browser talked to a web server and carried on some interaction. All those packets, instead of dealing with packets, we call that one flow. So we know the source, the destination, and the duration of that. The payload length is the length of the entire packet. The next header specifies what type of upper level packet is in the IP version 6 packet. So we can get some insight as to what's encapsulated in the IP version 6 packet. The hop limit is the same as time to live in IP version 4. And then, of course, we've already mentioned the source and IP addresses. Okay, here we have another video demonstration. This is going to be very similar to the one we saw just a moment ago with IP version 4, but it's going to be showing you information, like for starters, here is 0110, and that says, oh, that means we're using version 6 of the IP protocol. The other thing to notice that we haven't talked about before, I don't think, is an IP version 4 address is encoded into decimal dotted notation. Like 192.168.0.10. We've seen some IP addresses like that, but I don't know if we talked a whole lot about decimal dotted notation. Well, how do we represent 128 bits? So look at this crazy big number here. And in some cases, like this 0 here, is really 0000. So this whole thing right here is a IP version 6. So it is represented as hexadecimal digits. Every 4 hexadecimal digits has a colon between it. So if you thought IP version 4 was kind of hard to remember, this is a pretty long IP version 6 address. We will talk about ways to shorten it. Look at the destination. Notice that the destination is a lot shorter. So there are some shortcuts we can take to make those shorter, but we'll talk about those at the appropriate length and time. And I recommend that you watch this video outside of class. It's just a tad under 6 minutes long. Okay, 4146 is an activity that tests your knowledge of IP version 6 header fields. So this is like the activity that we just skipped over a moment ago, except it's IP version 6 instead of IP version 4. Okay, let's talk about what's called host forwarding decisions or routing. The network layer is responsible for directing IP packets between hosts. And those packets can be destined for a number of things. Right now they're just talking about unicast packets, it looks like in this section. But it may be destined for the host itself to something called the loopback address, which is 127.0.0.1. It can actually be any number that starts with 127, but most people use 127.0.0.1. One of my favorite t-shirts has on it that sometimes you see at IT or networking conferences says, "There's no place like 127.0.0.1." So a play on "there's no place like home." So the loopback address is the host itself. And a lot of times you would use that to talk to services on the machine, or you might ping that address. If you ping 127.0.0.1, the packet never really leaves the machine. It'll go down through the OSI model, through your Ethernet drivers, down to your NIC card, and then will immediately be returned back. So if you can successfully ping localhost, that means that your TCP/IP version 4 software is installed correctly, it is configured correctly, and it doesn't really tell you anything about the network itself or whether you are communicating successfully with the network. 127.0.0.1 is referred to as localhost. The localhost address. Now that'll be a little confusing comparing to what they mean here. I don't really like the fact that they use localhost here, but they're meaning a host on your local network. So in this case, we have a network here, and we have remote networks here, and this host is in the same network. It is whatever the network number is, .10 and .15 in this case. And .1 is the interface of the router that's in this network. The other thing you can be doing, which is shown by this top orange arrow, is you can be communicating with a remote host. That is a host that is on a different network. And again, the way we tell, or routers tell, that's on the different network is because it has a different network address. Or another way to say that is the network portions of the two hosts are not exactly the same. Routing is determining the best path to a destination, and routing is done on routers. in this case, when we have a network cloud or a specific network address, there is going to be an interface of the router that is in that network, and whatever that IP address is of this interface right here is going to be your default gateway or default router, whichever you want to call it, for every device in this network. Now, this router will have a different IP address here, being a different network. It might be .1 on that other network, or it might not be. It is very common to use .1 for the default gateway connection on a router, but it is not a required thing. It just makes it a little easier for network people to remember what the default gateway is if they're supporting that. And we'll talk about default gateway a little more in 6.2.1.2. So we talked about or saw an example of the responsibility of routing traffic off the local area network to other networks. It has an IP address that has the same network portion. We said that. And then what it does is it says it can take data in and forward data out. So the data in this case, this is a layer 3 device. We're talking about IP packets. The routing table that the router maintains has several different things. And a host has a routing table as well, which now that I think about it, I think this is what this is talking about. But in the case of a host, it has a route to the local address or the local host loopback address. It also has a local network route, and that is how to route packets to the same network. That would really just be what NIC we need to use. And then the local default route, which is going to be the address to the router for everything else that is not on the local area network. So that's what would be in a host routing table. So routers have routing tables, but hosts have routing tables as well. And we'll see in some upcoming assignments how to look at those route tables and how to decode the information. Okay, so this is talking about using the default gateway. This time they've actually shown you that the network number is 192.168.10.0. One thing they're showing you here that we may not seen before is we talked about subnet mask. For a Class C network, the subnet mask is 255.255.255.0. That basically means the division point is on the third period. Well, this is called slash notation, or sometimes CIDR, C-I-D-R, which is classless interdomain routing notation. But with the slash notation, they're basically telling you how many ones are in the subnet mask. So it would say there are 24 ones, which gets us up to this third period. So sometimes it's a little easier to use the slash notation, especially when we go to IP version 6. But basically, this PC's full address would be 192.168.10.10. This would be 192.168.10.15. And the default gateway on the router would be 192.168.10.1. So in the routing tables for these PCs and any other devices in this network, the default gateway would be the IP address of the interface on the router that is in that network, or this network is connected to, would be another way to say it. So we're on a Windows machine, we can see by the prompt, and we have a netstat-r command. The netstat command started in Unix, which existed before Windows, and the authors of the Windows operating system just used that because that's what computer people were used to. You can also say route space print on a Windows machine is another way to get it as well. But the netstat-r has a number of sections. So what will happen is it will have a list of all networks, or it'll have all of its interfaces. So notice that this machine appears to have local loopback address, but the IP outside is 192.168.10.10. If this machine had more than one NIC card, then whichever interface it should go out, it would have that IP address here. If it says on link, then that means it is on the local area network. And then if it's 0.0.0.0, that basically means any other host. So if it's any other host or any other IP addresses or network numbers other than the ones listed here, then I'm going to use my default gateway 10.1, which is also on my interface 10.10. So this will go through and show you a list of reachable networks that are currently in the IP version 4 route table. The one thing I didn't talk about is the metric. Basically, the metric is the cost of the route, and that might be how many routers it has to pass through, which would be called a hop count, which is one of the simplest types of routing decisions that's made, or it can be very complex calculations, and also takes into effect whether links are up and down, whether they're congested, and that type of thing. Okay, 6221 is talking about router decisions. So this is a little more complex. Notice we have a .10 network, a .11 network, and then we have some networks over here, which are 10.1.1 and 10.1.2. They're all using, even though 10 is normally a Class A network, which would be a /8, notice they are using a /24, so making it look like a bunch of Class C networks. So this router has 3 IP addresses: 192.168.10.1, 192.168.11.1, and here 209.165.200.225. So those are all directly connected network devices. Router 2 is the same way. It has 3 connected addresses. So that we will have the routing table for the router will factor in all the connections. Okay. So here's what a routing table looks like on a router, or more specifically an IP version 4. It has information similar to the routing tables, but it can have info on specific remote networks as well. So to display this, you see the command here, show IP route, and what it will tell you is it says the gateway of last resort is not set. Again, gateway of last resort is a term for default gateway or default router, and it doesn't have a default route set, which is fine. It does have you know that 10.0.24 is subnetted in 2 subnets. There are the 2 subnets over here. We get to them by going to this IP address. So that is the kind of information that is shown, and it also tells us which connection we need to go out. So either we need to go out gigabit 0/0, gigabit 0/1, or serial 0/0/0. So those are the ways on a router that we refer to the different interfaces. Okay, this is a 5-minute, 25-second video that's going to show you the displaying of the router tables and give you discussion about the information in there. So it'll cover what I just covered in the previous section, but I do recommend you go through and listen to that on your own. So what happens is in a routing table, in the first column, we have something referred to as the route source. And this tells how the route was learned. C means I am directly connected to this network. So that's how I know about it. L means it's a link local route. In column B, we have information about the destination network. These two networks are directly connected. And then in column C, we have the interface on the router that we need to use to get to that destination. So we talked about that previously. In the case of remotes, we have the router source that tells what protocol or how we learned it. A static route is a route that you put in when you configure the router, and it stays there and doesn't change. But we can have different ways that we learned it. This is the destination network, so if you need to go to any machine that has the IP address 10.1.1.something, this is the correct entry or the entry we're going to use for that. We have something called an administrative distance, which is a metric like we talked about before that would tell how many hops and or how much time, how speed differences, things like that are taken into account in the administrative distance. We still do have a metric. Lower values indicate preferred routes or routes that are going to be better. To get to this network, we do that via this IP address, which is called the next hop address. And then this is the timestamp. This is how long it's been since the router was last heard from. And then this again is the outgoing interface, the interface that the packet is going to be sent out to make it to its next hop address. Okay, so this talks a little bit more about the next hop address. So we have a highlighted router here, and what happens is it says if I need to get to 10.1.1.0, which is over here, from this router, if I need to go here, then I need to go to this router next, which should be 209.165.200.226. So when we're sending things through routers, it goes to the next hop router, which will route it to the next hop router, which will route it to its next hop router, until finally the IP packet makes it into the destination network and will be delivered to the destination host. Here's another video within Packet Tracer talking about the IP version 4. It's about 4 minutes and 50 seconds long, but you can go through to hear an alternate presentation on IP version 4 routing tables. And then 6228 is an activity that you can go through, and it has a definition, and then you can put a checkbox over in the right to identify, is it column A, B, C, D, E, or F that talks about or that represents what's talked about in the the 1 through 5 over here. So you can do that on your own to make sure that you're understanding things correctly. So section 6228, this activity, is where I wanted to make it to in this lecture. So I will end this for now, and then we'll continue on in a future lecture.